Have you ever thought about what it would be like to change the engine of a plane while it's still flying at 30,000 feet? Sounds impossible, right? Well, in the software world, that's basically what we're talking about today with hot code upgrades. We're going to dig into how the Erlang programming language pulls off this incredible magic trick, letting systems change and grow without ever having to stop.
So here's our flight plan. We'll start with the pain of the downtime dilemma, something we've all felt. Then we'll get into Erlang's secret sauce, its concurrency model, and how it uses modules. We'll see how state and new code get introduced, how it's all packaged up neatly with OTP releases, and finally, what it really means to build a system that can evolve without ever stopping.
All right, let's get real for a second. If you've ever run anything in production, you know this feeling deep in your bones. You've just finished a killer new feature or a critical bug fix. Awesome. But now you have to deploy it. And that almost always means one thing: taking the system offline.
And that leads to the million-dollar question, doesn't it? Your users don't care about your deployment schedule. Whether you're running a huge online game, a stock trading platform, or a critical piece of infrastructure, they just expect it to work all the time. So how do you push updates to a live system without kicking everyone off?
Just look at the difference here. On the left, that's the traditional playbook. You schedule maintenance, usually at some horrible time like 2 a.m. You stop the world, you push your code, restart everything, and just hope for the best. And right there in the middle is the big, ugly problem: downtime. But on the right, the Erlang way is just different. It's a smooth, controlled upgrade that happens while everything is still running. No drama, no downtime.
So you've got to be asking, how is that even possible? It's not some fancy add-on library or a complicated deployment script. Nope. The secret is baked right into the DNA of Erlang itself. It all comes down to its secret sauce, how it thinks about concurrency.
Okay, first thing to know. In Erlang, everything happens inside of something called a process. Now, you've got to forget everything you know about operating system processes. These are not those. Erlang processes are ridiculously lightweight and completely isolated from each other. You can spin up millions of them without breaking a sweat. They're the fundamental atoms of any Erlang system.
And this right here is the absolute key to everything. A process's state, the data it's holding in memory, is totally separate from the code module it's running. Think about it like this. You have a worker, and you have their instruction manual. The worker and the manual are two different things. This means you can swap out the manual for a new one without stopping the worker. That simple idea is what makes hot code upgrades possible.
So separating state in code is a superpower. But to make it actually work across a big, complex system, you need some rules. You need a standard way of doing things. And that's exactly where OTP behaviors come into play.
Behaviors are basically just blueprints for common types of processes. The most famous one is called Gen Server, for a generic server. Instead of building a server from scratch, Erlang gives you this battle-tested generic foundation. All you have to do is provide the specific bits of code, the callbacks, that make your server do its unique thing. And having this standard is so important. When all your stateful processes are built using a pattern like Gen Server, the whole system knows how they work. They're predictable. And because they're predictable, the system knows exactly how to upgrade them without messing anything up.
Okay, let's recap. We have our tiny little processes. We know their state is separate from their code, and they're all built using a standard structure. So, now for the big reveal. How does the old state get safely handed over to the new code?
So just picture it. We've got our little Gen Server process just chugging along. It's running version 1 of our code, it's got some important data saved in its memory, its state, and it's just happily doing its job, handling requests.
And there it is, the bridge. The entire magic trick comes down to this one special function that you write, code_change. This is the formal, official handover point between the old version of your code and the new one.
Let's walk through the magic trick. First, the system loads your new code, version 2, into memory. Version 1 is still there too. Then, when it's time to upgrade, the system tells the process to get ready. And here's the crazy part. It calls the code change function that's in your new code, and it passes in the current state from the old version. Your job, inside that function, is to convert the old state into whatever format the new code needs. Once you do that, the process just picks up right where it left off, but now it's running version 2 with the perfectly preserved and transformed state. Seamless.
Now that is incredibly cool for a single process. But a real system isn't one process. It's hundreds, maybe thousands, spread across different services. So how do you coordinate and upgrade for the entire system? Well, for that, we need to talk about OTP releases.
First, we take all the code modules that work together for a specific feature, like, say, a user database, and we bundle them into what's called an OTP application. It's like a self-contained component that you can start and stop as a single unit.
Then you take all of your applications, plus the core Erlang system itself, and you bundle all of that into a complete deployable system called a release. So if an application is like a single app on your phone, a release is like the entire iOS or Android system update. It's the whole shebang.
And you don't have to figure out how to deploy this stuff on your own. OTP gives you a whole professional toolkit called release handling. This thing is smart. It understands dependencies, it manages the upgrade from one version to the next, and get this, it can even manage a downgrade if something goes wrong, all while the system is live.
So, after all that, what's the big takeaway? What's the ultimate payoff for all of this clever design?
Honestly, it's so much more than just a neat feature. It's a whole different philosophy for building software. You stop thinking about big, scary, risky deployments. Instead, you start thinking of your system as a living thing that's in a constant state of low-risk, continuous evolution. It's a mindset built for systems that absolutely, positively cannot go down.
And that's the bottom line, right there. This isn't about making your deployments a little bit faster, it's about completely eliminating a whole class of downtime. Hot code reloading means the system can evolve, grow, and improve continuously with zero downtime.
So I'll just leave you with this one question to chew on. Imagine for a moment that scheduling a maintenance window was something you never had to do again. If downtime for updates was just gone, what could you build then? What kind of amazing things would that make possible? It's pretty incredible to think about. Thanks for watching.